Hello everyone and welcome back to Greenstat Hydrogen webinar series. I'm your host Prasadini Wickramasinghe. I am an energy analyst and I coordinate our activities at Greenstat Hydrogen in Sri Lanka. It is wonderful to see many of you joining us today from different parts of the world. Thank you for your time to be here with us today. Today's webinar is titled Technical Pathways for Lower Pressure Green Ammonia Synthesis and Expansion of Applications. As the world transitions towards cleaner energy, green ammonia is increasingly in the spotlight, not only for its potential as a hydrogen carrier, but also for its broad industrial use. However, challenges still remain in improving production efficiency and exploring wider applications. We are privileged to have two expert speakers from KAPSOM with us today. Yuan Wu, the marketing manager at KAPSOM. Yuan brings a deep understanding of market trends and the practical adoption of green ammonia technologies worldwide. Zhixiang Chao, the R&D engineer at KAPSOM. Zhixiang is at the forefront of research and development, particularly in membrane separation technologies for low-pressure ammonia synthesis. Before we start, let me quickly introduce who we are. Greenstat is a Norwegian company focused on building a greener world through renewable energy, especially green hydrogen. Our Center of Excellence for Hydrogen here in Sri Lanka supports knowledge sharing, capacity building, and global collaboration. We work closely with universities and international experts to promote hydrogen safety, technology, policy, and the full value chain. We also invite you to stay connected with us and follow us on LinkedIn for updates on our projects, webinars, and partnerships. Subscribe to our YouTube channel where we upload past webinars. Also visit our website to see more information. We are especially pleased to be hosting today's session in collaboration with KAPSOM, a leading company in modular plant engineering and pioneer in green ammonia production technologies. KAPSOM is recognized for its innovation in process optimization and scalable solutions for clean energy industries. Their expertise significantly contributes to advancing the hydrogen economy. Without further ado, let's dive into today's session. Yuan and Zhixiang, the stage is yours.
Okay, so I'm going to start today's sharing of this webinar. Hello, everyone, and thank you for joining today's webinar. I'm Yuan, the marketing manager at KAPSOM. Today, my colleague and I will share KAPSOM's achievements in green ammonia synthesis over the past decade, as well as our current R&D focus and future directions. My part will serve as an introduction, after which I will hand it over to Zhixiang, our R&D manager, who will delve deeper into green ammonia technologies. So first, let me briefly introduce who we are. KAPSOM was founded in 2013. Initially, we operated primarily as an EPC company, but since 2017, we've shifted our focus to green chemical engineering and innovation. So our headquarters are located in Nanjing, a city in eastern China. This is a region known for its strong economic development. And Nanjing also boasts a well-developed chemical industry foundation. And we warmly welcome you to visit our office, factory, and R&D center. To facilitate global business, we also have offices in Hong Kong and Singapore. Additionally, as South America and Australia grow increasingly important in green chemicals, we are exploring the possibility of establishing offices there. So now let's dive into today's topic, green ammonia. You might wonder, why did KAPSOM make this strategic shift towards green chemicals? And why focus specifically on green ammonia? The answer starts with the undeniable global energy transition. Over the past decade, we've seen historic commitment to decarbonization. In 2015, the Paris Agreement united 196 countries in limiting global warming. By 2020, the EU launched its trillion-euro Green Deal. And in 2022, China pledged to achieve peak carbon dioxide emission by 2030. The European Commission has recently unveiled the draft European climate law, legally enshrining the 2050 carbon neutrality target, and China's target of carbon neutrality is 2060. The message is quite clear. The future is low carbon, and green ammonia is a critical piece of the puzzle. So why? Because it's everywhere. In fact, over 180 million tons are produced annually, feeding half of the world's population through fertilizers. Yet, traditional methods emit nearly 2 tons of carbon dioxide for every ton of ammonia, contributing almost 2% of global emissions. That's unsustainable. So green ammonia made the renewable energy slashes emissions by 90% or more. It's not just an option, it's obviously the only way forward. So why us? Why KAPSOM? First, our deep ties to China's top engineering schools, like Nanjing University of Technology, gives us unmatched access to cutting-edge research and talent. And second, our team blends decades of industry experience with fresh innovation from elite graduates we recruited from universities like Tianjin University, which is also a top-notch school in China. And third, we've spent over a decade ramping up R&D investment, testing advanced technologies, and fostering a culture where every employee contributes to ideas. In short, we see the future, we've built the team, and we're investing to lead it. Actually, we all recognize ammonia synthesis as one of the chemistry's landmark achievements. In fact, the Haber-Bosch process has produced most of the world's ammonia today, is celebrating its 112th anniversary this year, having been developed in 1913. While this century-old technology feeds half the global population through fertilizer production, its energy intensity remains staggering, consuming about 1% of the world's total energy output to maintain the high temperatures and extreme pressure required. This creates both a challenge and an opportunity. How do we honor this chemical engineering milestone while fundamentally reinventing it for the net zero era? On this critical question of reducing energy consumption and optimizing reaction efficiency, where we see potentially 20 to 30% efficiency gains through emerging technologies. My colleague Zhixiang will share groundbreaking approaches in his technical deep dive later. So currently, KAPSOM is pioneering green ammonia projects across the continents. Our installation in India, Saudi Arabia, Colombia, and Namibia each represents their region's first green ammonia facilities. These aren't just projects, they are making industrial history. Actually, beyond ammonia, we are breaking new ground in sustainable fertilizers with Africa's first green fertilizer production. And we've recently achieved a milestone you may also have read in the industry news, the world's first inaugural industrial-scale green methanol plant. When European Energy produced their first drop of carbon-neutral methanol, the groundbreaking molecule has KAPSOM's fingerprint on it. What makes this project extraordinary? Consider the Namibia small-scale facility alone will display 2,000 tons of CO2 annually, equivalent to taking 1,000 cars off the road, while the e-methanol project creates a blueprint for decarbonizing maritime fuel at a time when shipping accounts for nearly 3% of global emissions. Indeed, you may have already sensed, we are not just observers of power-to-X revolution, but passionate architects shaping its future. Now, speaking of fertilizer, where 80% of global ammonia production ultimately flows. This precisely why KAPSOM has made green fertilizer equipment a top R&D priority. We are betting big on this sector because the numbers don't lie. Every 1 ton of green ammonia used in fertilizers prevents 2.5 tons of CO2 emission compared to conventional methods. But ammonia's potential extends far beyond agriculture. We recognize ammonia's role as the most efficient hydrogen carrier, with 50% higher energy density than liquid H2. That's why we are simultaneously developing next-generation ammonia cracking system. I'm proud to share that our pilot-scale ammonia cracking unit produces hydrogen with a purity of 99.997% and a residual ammonia level below 0.01 ppm. For those interested in technical depths of catalyst and membrane separation that makes this possible, we'd be delighted to do a deep dive session in the future. In China, we have an old saying, if I put it directly, it means one step ahead, always ahead, which means if you are lucky or wise enough to grab the early opportunity, it will lead you to the lasting dominance. Today's presentation was about more than just sharing knowledge and practice. It was about handing you the keys to lead this revolution. At KAPSOM, we're not just building equipment, we're building the infrastructure for net zero future. This question isn't whether green ammonia will transform our industry, but who will transform it first. That who could very well be you, working along with us. Now I will pass my microphone to my colleague Zhixiang, who will take us from probability to practice with his technical breakdown. Please.
Hello, everyone. I'm Zhixiang, a research and design engineer at KAPSOM, and I'm really glad to have the opportunity to communicate or maybe brainstorm with you at today's Greenstat webinar. As we know, ammonia synthesis is a fairly classical chemical process, as shown in Figure 1. In the conventional Haber-Bosch process, 400 degrees Celsius reaction temperature and 10 megapascal are generally required to meet the need to carry out the reaction efficiently within kinetic and thermodynamic constraints. At the ammonia separation stage, an ammonia cooling system below -10 degrees Celsius is usually required to liquefy the ammonia gas, where unreacted hydrogen and nitrogen are circulated back into the reaction system for usage. In recent decades, numerous studies have been conducted on enhanced ammonia systems, and the realization of efficient ammonia synthesis under mild conditions will be a long, difficult, but fascinating topic. As shown in Figure 2, these studies mainly covers the following topics: novel synthesis catalysts, electrochemical reduction, plasma catalysts, chemical chain cycles, separation-enhanced reactions, and so on. Although most of these research are still at the laboratory stage, we still believe that there exists some solution to apply these attractive results to industrial practice, and we, KAPSOM, are committed to this goal. In the following part, I will present the combination of membrane separation technology with ammonia synthesis, aiming at reducing the overall energy demand. As shown in Figure 3, a gas membrane separation process replaces the traditional ammonia cooling. The ammonia gas is directly separated from a mixture and sent to liquefaction. The hydrogen and the nitrogen recycle and mix with fresh gas. So now first, let's go back to 1992, when Professor Kessler introduced the concept of membrane separation for enhanced ammonia synthesis using an ionic modified naphtha membranes, which demonstrated very high selectivity for ammonia and nitrogen separation. As shown in Table 1, we can see when temperature increases from 25 to 200 degrees. These membranes basically maintain good selectivity, but the permeation rate is significantly lower, implying a larger membrane area required and higher investor cost. In addition, we know that after the reaction in the heat exchanger, the temperature mostly reduced to 200 to 215 degrees, and the naphtha membranes usually have a carbon backbone stable to about 214, which may cause some risk in practical industrial applications. It can be said that the structural instability at a high temperature is the usual drawback of organic membranes. In recent years, more and more scholars have developed ammonia separation membranes with increasingly superior performance, making the coupling of membrane separation and ammonia synthesis more and more realistic, as illustrated in Figure 4. In this picture, we can see that one of the special materials, the molten salt membranes, combines high temperature stability with excellent selectivity and ammonia permeation rate. Seems to be the ultimate goal we are pursuing. However, as the partial pressure of ammonia increases, the performance of ammonia rapidly decreases, like shown in Figure 5. It may limit the usage in ammonia synthesis for the high reactive pressure. Last year, we cooperated with the Nanjing University of Technology and did some research work. Due to laboratory constraints, we temporarily used water instead of ammonia because of similar molecular dynamics, diameters, and the physical saving mechanisms we used. The molecular cell membranes were taken from the separation of gas mixture of water, nitrogen, and hydrogen, which demonstrated excellent separation, selectivity, and high permeability. From Figure 6, we found that with a higher pressure drop up to 1.2 megapascal, the permeability increases significantly first, then stabilizing while maintaining a nearly 100% gas purity. With gas temperature increases, despite the permeability of water increases significantly, the concentration of water at the permeable side decreases obviously. This may be attributed to the expanse of the pore size at higher temperatures as well as the increased diffusing of hydrogen molecules. In all, the performance of the membranes needs to be considered comprehensively. It is necessary to carry out stability tests for a long enough period of time under industrialized conditions of use, and the development of sufficiently stable and efficient membrane materials for ammonia separation is not a simple matter, and it still requires a great deal of time and resources. Last month, we have built our own research center and continue to invest efforts to validate the feasibility and the improvement of the technology. Apart from the use of membrane separation instead of ammonia-cooled separation, we believe the ultimate form of coupling membrane separation and the reaction must be an integrated one, such as a membrane reactor. Continuous separation of ammonia gas during synthesis could bring the thermodynamic limitation of ammonia synthesis reaction. But at the same time, it has higher requirements on the mechanical properties of materials, such as operated temperature over 400 degrees. We have not yet succeeded in developing materials that meet the requirement, but some simulation work has been done. As shown in the figure 7, the use of a membrane reactor can continuously promote ammonia generation even at a pressure of 3 megapascal. The conversion rate based on nitrogen can be increased from 17% to 45% at the same space velocity. However, an easily overlooked requirement of the membrane reactor is the need to provide sufficient membrane spiration area within the limited reactor space, so the hollow fiber membranes was preferred. Otherwise, the ammonia in the residual side gas needs to be removed additionally, which could bring extra requirement and energy consumption. In this condition, we build a theoretical model of an ammonia synthesis system combining a membrane reactor and a membrane spirit, which operated at 3 megapascal, as shown in figure 8. Ammonia gas in residual side gas is spirit by a membrane spiration device and then mixed with ammonia from membrane reactor, then into liquefaction unit together. When we use membrane spirit technology in ammonia synthesis, a non-negligible problem is the additional energy consumption required to liquefy the ammonia gas. For example, if the residual side gas is pure ammonia and under 1 atmosphere and 200 degrees, the temperature should further decrease to about -18 degrees Celsius or room temperature and then compress to 1 megapascal. Therefore, we believe that a better approach is to directly use ammonia gas as a medium for downstream utilization, such as green fertilizer synthesis. When it comes to green fertilizer, we have also conducted some research, such as the preparation of MAP or DAP from ammonia and phosphoric acid, as shown in figure 9. We used a macro reactor with the inner diameter of 1 millimeter and the length of 18 centimeter. The total flow of acid and base was 85 milliliter per minute, and the state time was less than 1 second. From the figure 10, it could find that we can accurately adjust the pH of the product simply by adjusting the acid-base mass ratio of the feed material. The production is liquid, which then cooled and dried, and finally we got the corresponding fertilizer crystals. It is worth noting that the concentration and the flow rate of raw materials, as well as the reaction temperature, need to be carefully matched. Otherwise, it will lead to clogging of the channel like figure 11. The most obvious advantage of a microreactor is the minimal reaction time and the price ratio control of the reaction ingredient, as well as the more compact footprint. Furthermore, we are currently implementing a distributed green fertilizer plant which also employs a micro device to produce ammonium hydroxide and liquid ammonium sulfate fertilizer for fruit and vegetables such as tomatoes. The production rate is nearly 2,000 tons per year. The micro-channel reactor we use in this project has a heat transfer area of 4,500 square meters per cubic meters, and the total heat transfer coefficient up to 2015 watts per meter Kelvin, which is 100 times more than conventional reactors. This ensures the heat generated by the reaction can be carried away in a timely and efficient manner. Above all, we always take innovations as the core driving force of enterprise development and aim to give you, our customers, better solutions. So if you have any ideas expectation or confusion about the future of the green ammonia industry, please feel free to share them with us. The email address is shown on the slides. That's my presentation for today. Thank you very much for listening.
Okay, actually very thankful to Zhixiang to give this presentation. He quickly go through what we did in the past years and what we are planning to do in the future in terms of green ammonia and its downstream applications. And actually, just as he said, we care a lot about our customers' real needs. So during our daily communication with our customers, actually, we will ask them lots of questions. What their true need is, and from their own market, what kind of opportunity they have sensed, and we really like that kind of communication. That's why we have our email address here. So in the future, if you have any questions or anything you just want to discuss with us, it's welcome to send us email, or just as I said, if you want to pay a visit to Nanjing in China, in our office or R&D center or factory, is all welcomed. Okay, so looking ahead, I think it perfectly illustrates our core belief for today's presentation. While ammonia synthesis may be a centuries-old science, breakthroughs in materials and process engineering are rewriting its future every day. So at KAPSOM, we embrace our role as a very nimble and very flexible innovator, where clients need to don't just guide our R&D, but they feel it. Just as I said, they care about it. We really care about our customers. So that's why we're committed to keeping this conversation going on with all of you, learning more about your challenges or co-developing solutions, and ultimately turning today's green ammonia potential into tomorrow's carbon neutral reality. So I think this is basically the end of our today's presentation. I'm not sure whether I should give our microphone to our hosts. I think the following time will be Q&A. Is it? Should I just stop sharing my screen?
Hello. Thank you very much, Yuan.